Welcome everyone. Today's lesson is entitled Complex Numbers. Now if this was an Algebra 2 class, we would walk through this introduction to these complex numbers in a much more formalized and gradual way. But because this is a pre-calculus class and you do have some foundation with complex numbers, you're going to get very much the abridged version of the introduction. So I'll try to go through this relatively fast, but by providing some context, and that'll save us some time as we get into all the operations of complex numbers, which you're going to really need to know as the lesson kind of coalesces and continues on to the end. All right, so let's start the investigation up at the very top there, and it does just state what type of number is needed to represent the solution set of each equation. And again, I don't really care about what the answers are. I care about what type of number do we need to solve this type of equation. And again, I won't go back into the history of mathematics and all these different types of numbers, but I will start with really the most basic subset of numbers, which would be the counting numbers. Counting numbers are 1, 2, 3, 4, etc., right up the line. And if I look at that set of numbers and I look at this equation here, there is no value in the counting numbers that would make this equation true. So counting numbers are not satisfactory in order to solve this equation. So I need a different type of number. Okay, then I would maybe take a step up and I'd look at whole numbers. Whole numbers would be 0, 1, 2, 3, 4, etc. And as you can see, that set of numbers wouldn't allow us to solve this particular equation. So I need to go up another step and I'd say, all right, well maybe integers. Integers would be 0, 1, 2, 3, 4, but also -1, -2, -3, etc. And again, nothing in that set of numbers would allow us to solve an equation like this. And so I need a different type of number. And so I would go up maybe one more step, and I would get into what are called rational numbers. And so rational numbers, and that will kind of do it here, rational numbers are any numbers that can be written as a fraction. And that's what I need here. We know obviously the answer is 1/2. It is a fraction. And a rational number in decimal form, as we know, of course, would have a decimal that either terminates or repeats. So like 1/2 is 0.5, so the decimal terminates. If the answer was 1/3, that would be 0.3 repeating. So those are irrational numbers. Okay, so we have a different type of number outside of the ones that I had said initially that would allow us to solve this particular equation. All right, and then I go to the next one, x squared equals 2, and I would probably try to undo the square there and take the square root of both sides. And unfortunately, as I kind of look up, there's no rational number actually that would make this equation true. There's no fraction that I can put in place of x that if I squared it would give me 2. So I need a different set of numbers in order to solve it. And as we know, this would be what is called an irrational number. And so an irrational number, by definition, is a value whose decimal does not terminate, nor does it repeat. Okay, so the rational numbers and irrational numbers together form what is called the real number system. Okay, and then I get over to this last one over here, and same idea. I would probably try to undo the square and square root both sides. But essentially, I would get to a point where I'm looking for some number squared equal to -1. Well, I think about it as a positive number squared is going to give me a positive. A negative number squared also gives me a positive. So there's no value in the real number system that allows us to solve this particular equation. So we need to expand our sets of numbers in order to solve this. And so when we expand it into what is called the imaginary number system. So we need a different type of number. Since the real numbers don't suffice, we use an imaginary number in order to pull that off. All right, and again, you've kind of seen this before, but I just wanted to highlight that idea, that classification of numbers. And so rational and irrational make up the real number system, and there is no real number to solve this equation right here. And so we need a different type in order to do that, and it opens up the doors to our imaginary number system. Okay, and it all stems from the imaginary unit, denoted by I, of course, which you've seen before, and I is defined as the square root of -1. If you can please go ahead and box that up for me. And so by definition, I is equal to the square root of -1, which means, and I'm going to go ahead and square both sides. So if I square the left side, obviously that's just I squared. And if I square the right side, think of that, squaring the right side, the square and the square root would cancel, and so I end up getting -1. So immediately we can connect I right back to the real number system as I squared is equal to -1. So I don't know, just somewhere out there, put a little asterisk behind that one, because you'll definitely need to know that piece. All right, and the complex numbers. So the number system that results from introducing the number I, and the standard form, as we potentially know, of a complex number is A plus BI. And the A represents the real part of the complex number, and the BI would represent the imaginary part of the complex number. Okay, so A plus BI, we're going to focus most of our attention dealing with the operations around A plus BI. A is the real part, the BI represents the imaginary part, and now everything fits under the umbrella of being a complex number. All rational numbers are complex numbers. All irrational numbers are complex numbers. All imaginary numbers are complex numbers. All right, and so what type of number do we get when B is 0? So if the B value is 0 here, this kind of disappears, and we're just left with A, which obviously then would just be a real number. Excellent. And what type of number do we get when A is 0? Well, we would kind of say it as we get a pure imaginary number. Okay, and really, even when A is not 0, as long as B is not 0, we'd still consider that an imaginary number. So anytime really that B is not 0, it fits in the realm of being an imaginary number. Okay, so we'll just try to classify it in a little more detail there. If A is 0, it's more like a pure imaginary number, but it definitely fits under that complex number system. Okay, perfect. So again, we do want to get into our operations dealing with complex numbers here, which again, you've seen before. So some of this is going to be review, maybe a little expanded towards the end of the lesson here. So first two operations we will perform, of course, will be the adding and subtracting. And here's how I just kind of think about it is you're really just combining like terms. And I'm just going to put the like terms sort of in quotes there. What I essentially mean by that, everybody, is you're going to combine the real parts together, and then you're going to combine the imaginary parts together. And so we'll just do this one right here. So I have 8 plus 4i, so again, A plus BI, and then minus another complex number. So I've got 10 minus 2i. And so as I said, I combine the real parts, and I combine the imaginary parts. So I think of this very simply as positive 8 minus 10. That'll give me the real part. And then 4i minus negative 2i in order to get the imaginary part. All right, so don't overthink the adding and subtracting. As soon as you see that symbol in between the two, you know just combine the real parts together, combine the imaginary parts together, and should be good to go. So long story short here, should be negative 2, and looks like plus 6i would do the trick. All right, box that one up. 2 operations in the books already. Let's get into the third operation, which would be the multiplying complex numbers. And so the way you're going to play this out, everybody, is either you're going to distribute or FOIL, just depending. And one thing to note, make a little asterisk if you would. Please remember, because you're going to definitely see this, I squared equals negative 1. So as soon as you see that I squared, we're going to change that to its equivalent form as negative 1. All right, so we'll do 2 of them. one with more of a distribution of this pure imaginary number into this more comprehensive complex number there. And then the second one will be two complex numbers FOILed out together. All right, so without further ado, boom, bring that on in. And it looks like I'll get negative 15I and minus 3I squared. Now again, should pop up right away as soon as you do see that I squared. We do want to change that to negative 1. Now you could probably do this a little quicker than I'm about to do it, but just in case, especially as this is the first time, I'm going to just put it here as negative 1. So just seeing that all that happens is that I squared becomes negative 1. And now I can kind of clean this up a little bit. So the real part of our complex number comes from this, and that would be positive 3. Typically you would see that out in front. And then it looks like minus 15I on the back. So real part and imaginary part. Excellent. Let's move on to part B. And so now we're going to FOIL. So let's bring this together. So I got a 2 times 3, which is 6. Outside, 2 times negative 4I. So that should be negative 8I. Inside, positive 5I times 3. So that should be a 15I. And then last, it looks like 5I and negative 4I. So I'm getting negative 20I squared. And again, just as the teacher, I want to make sure all the steps are really accounted for so I don't lose you. If you can clean this up a little quicker, by all means. But I'm going to go ahead and take an intermediary step right here and think of this part. So that would be negative 20. The I squared is negative 1. So I am hoping you see this right here as positive 20. That's the key. And so when I have the positive 20, and again, just I should be as clear as I possibly can here. Don't feel obligated to write that down. But that's how it plays out with I have two pieces of the puzzle producing the real parts, here, and two pieces producing the imaginary part. So I'm getting 26, and I'm getting a plus 7I. All right. Again, if you need to write this stuff down, step 2, step 3 here, by all means. If you can kind of jump from here to here, that's fantastic. All right, so multiplying, that would be our third operation. Just please do remember that piece right there, I squared as negative 1. On to my next board. So one little preliminary step before we get into more of the division, which would be our fourth operation. So there's a term and a notation that we're going to need to kind of highlight this next piece. So it says what is called a conjugate. So conjugates of complex numbers. And so if we have a complex number, when you start to take some higher level mathematics, you see complex numbers denoted with the z. So I just initiated that right here. So if z is equal to a plus bi, then the conjugate is z with a little line above it. That's how we talk about the conjugate. And so again, here's the complex number talking about its conjugate. And very simply, the conjugate of any complex number keeps the same real part, but changes the imaginary part to its opposite. So that's exactly what you're going to write here. As simply as it gets, a conjugate, same real part, opposite imaginary part. And what we're going to do is just highlight that with an example 3 here momentarily. Again, don't overthink this. It's going to allow us to do some operations moving forward. But for right now, the conjugate, when you hear that term, same real part, opposite imaginary part. So why don't you take literally 10 seconds, see if you can knock out A, B, and C. I'll wait a sec. You can pause, whatever the case may be. And all I think about, same real part, opposite imaginary part. So the conjugate of 4 plus I is 4 minus I. The conjugate of negative 3 minus 2I is negative 3 plus 2I. The conjugate of negative 4I is just positive 4I. Same real part, opposite imaginary part. Now, here's what's kind of cool. I like this one. And this is sort of the rationale for introducing the idea of a conjugate. It says what type of number is produced when you do multiply two conjugates together. So watch what unfolds here. I'm going to just do this off to the side. Actually, no, I'm going to do it right here. So if I do this, you kind of get a times a, so you get a squared. Okay, and then you get like a times negative bi, so that would be negative abi. And in the inside, you kind of get a times positive bi, so you kind of get that. And in the last, you would get negative b squared I squared. And that looks pretty complicated, but let's see if we can simplify this up a little bit. What jumps out to me, of course, is look at the middle. Both terms that produce the imaginary part are opposites of one another. So don't these guys just cancel out? And then I'm left with negative b squared I squared. Well, hey, of course, isn't I squared just negative 1? So now that this is negative 1, doesn't this change that to just plus b squared? And so, a long story short, what happens is you just get a real number. Anytime you multiply two conjugates together, you just get a real number, and that real number happens to be, and you can, when you're going to do this in a little bit, you can shortcut if you remember this little pattern, but it turns out to be a squared plus b squared. It's kind of cool, actually. So if we need to somehow change an imaginary number into a real number, this little algebraic trick allows us to do that by creating the conjugate and multiplying them together. Okay, so that is going to lead us into our fourth operation. So reciprocals, we'll talk about those momentarily, but essentially it comes down to division. And so division of two complex numbers is not sort of the conventional way you've thought about division. It's not thinking, oh, well, how many times does the divisor go into the dividend? It's not really how we're going to think about it. What we're essentially going to do is just try to write it in a plus bi form. So what it comes down to, everybody, is we're going to eliminate I in the denominator. So the denominator of a fraction is considered the divisor in the division operation. And so what we're going to do, by eliminating I in the denominator, we then immediately get it in the form we want. We get it into a plus bi. So your rule of thumb, and if you would, so you're going to use I for a pure imaginary number. I'm just trying to parse this for you as best I can. So for a pure imaginary number, and use conjugate for more of a comprehensive complex number, for lack of a better description there. So I'll just kind of do it as complex number with a not being 0. So if a is 0, we're going to use I. If a is not 0, we're going to use the conjugate. And again, you're kind of looking like, oh, well, what does that exactly mean? I promise, obviously, I'll show you here in the next couple minutes with our next example. All right, so the fourth operation really deals with the division algorithm. So example 4, starting it out. And just kind of keep in mind, it's funny, I've taught this for many, many years. Reciprocal is different than conjugate. I just want to be very clear about that. We're going to use the conjugate to answer this question momentarily. But when I say to you, find the reciprocal of a number, reciprocal essentially just means we're flipping the number. So, and don't write this on your paper, but this is the number. Any value can be written over 1. And so the reciprocal of it is this right here. So this is what you write on your paper. That's the reciprocal of 2 plus 5i. Okay, so if you would, please go ahead and make sure that's written down. And the idea essentially is working with complex numbers to eliminate I in the denominator. And that's essentially what I have here. I have this I in the denominator. Does everyone see that all right? And so we need to represent this in a more conventional manner. And so that's what we're going to do. We're going to change this from having 1 over 2 plus 5i. We're going to change it into its a plus bi form. So I'm not actually doing the operation of, well, how many times does 2 plus 5i go into 1? what I'm going to do is just concentrate on eliminating I in the denominator, and by default, it will perform the operation. Okay, now if you look on my last board, it says use conjugate for a complex number when a is not 0. And that's exactly what I'm going to do here, everybody. So what I'm going to do is I'm going to multiply that denominator by its conjugate, right? Because that will change it to a real number. Multiply two conjugates together, and you get a real number. Well, anything I do to the denominator of a fraction, I, of course, need to do to the numerator. And so I do that right there. And so what that means is I'm changing the form of the number, but I'm not changing the value of the number. And that's the goal here. All right, so let's see what happens. So 1 times 2 minus 5i, well, that's obviously just 2 minus 5i. That's not too bad. Now, watch what happens here when I FOIL this. So I won't follow my pattern, but I will just FOIL it. 2 times 2 is 4. Look at the outside and inside, everybody. I got negative 10i on the outside, positive 10i on the inside. Those cancel, which is exactly what we wanted. And in the last, I would get minus 25i squared, which now, everybody, we should realize that is just plus 25. That's negative 1, so that should be plus 25. And so what I'm starting to get is 4 plus 25, which is 29. Now look, at this stage, if you left it like that, I can live with it. I'd give you credit for it. But what I'm going to ask you to start to think of is really formalize that a plus bi. And sorry, that should be a minus there. So the real part, because this is just a common denominator to both parts here, so it's 2 29ths minus 5 29ths I. A plus bi form. That's the reciprocal of this right here. Alrighty, so as I said, if you can write it like that, so be it. I'd prefer you trying to write it like this. If you start taking sort of the next steps in mathematics, there's some really interesting visual aspects of complex numbers, and it helps to see the real part and the imaginary part separated. Okay, on to example 5. Perform the operation. So here again, we have division. 2 minus 3i divided by 4i. And all I'm going to focus on is just getting rid of the I in the denominator. So as it said on my last board, for a pure imaginary number, where again a is 0, I'm just going to use I. So you can use a conjugate. It is simpler for a pure imaginary number just to use I. Because remember, the goal is just to turn this into a real number on the bottom. Once I do that, problem solved. And so I could do negative 4i here, but it's sort of unnecessary, because if I just do I, then right away you can see the denominator is 4i squared, which of course is a real number. That's just going to be negative 4. All right, I'm hoping you see that. So use I for the pure imaginary number down there. Now I'm going to distribute that into that, and so I get, what's that, 2i and minus 3i squared. I'm going to clean this up a little bit. Again, this would not quite be satisfactory just yet. I want to see how far we can go with this. I'm going to leave the 2i for the moment. But I'd hope you'd agree that this would be a plus 3, because here's negative 1 times negative 3. So there's the 3. And in the denominator there is the negative 4. So remember, everybody, this is good. I want to see if we can go a little further. So think about a real part, imaginary part. This is the common denominator to this and also this. So as I look at it, I get a 3 over negative 4. So that would be just negative 3/4. And then I get a 2 over negative 4. And I hope you're okay for 2 over negative 4. That would reduce to 1/2. So it's negative. So that's why that's a minus. So it would be minus 1/2 I. All right, so negative 3/4 minus 1/2 I. Cool. So let's box up kind of our answers here just to really highlight what we're going for at this level. Again, algebra 2, yeah, you leave it like that. Let's see if we can move it up a notch. Let's see if we can be able to take that next step forward. All right, so we've got 4 operations in the books. Now let's talk about some of the exponents, specifically just with that imaginary unit. And this is kind of cool to see. And again, I won't take too long with this, but I'd encourage you to try to jump ahead a little bit and fill some of these blanks in. It's fascinating the way, patterns in mathematics. It's really interesting to see. So I started this out. A couple things we already know. Obviously, I to the first is just I. It goes without saying. I already defined I squared as -1. What about I to the third? Well, using exponential properties, I know that I squared times I to the first, because 2 plus 1 is 3, using my exponential properties, I know that this is equivalent to I to the third. Well, hey, look, we see it right here, right? Isn't I squared just -1? And isn't I to the first just I? So are you okay with me saying this and you seeing it, but this would be just -1 times I. And if I do -1 times I get -I. All right. Now what if I did I to the fourth? One way to look at I to the fourth is saying something like I squared times I squared. Again, 2 plus 2 is 4. Exponential property fits. Well, I squared times I squared. Okay, well that's just -1 times -1. And -1 times -1, there we go. We just get +1. All right, so I want you to see this. I, -1, -I, 1. Watch what happens here, especially now that I know I to the fourth is just 1, right? So I just defined that right here. This is just 1. So I got 1 times I to the first. Isn't that just I? I have 1 times I squared. Isn't that just -1? I have 1 times I to the third. Oh, well, there's I to the third. Isn't this just -I? And then I have 1 times I to the fourth. Well, of course, just 1 times 1. And look at that. Could I then go ahead and do the same thing next time around? I to the eighth is 1. So couldn't I do that right here? 1 times I. Hey, wait a minute. Are we starting to see the pattern just continues? And couldn't I do this on and on and on? Absolutely. So the moral of the story here, I suppose, is powers of I repeat in a cycle of 4. And our cycle is I, -1, -I, 1. I'll repeat that. I, -1, -I, 1. So if I wanted to know I to the any power, all I need to know is where in this cycle of 4 would it be? Would it be here? It's I. If it's here, it's -1. If it's here, it's -I. And if it's here, it's 1. So we divide the exponent by 4 and determine the remainder. If the remainder is 1, then we're in the top row, guys. It's just I. If the remainder is 2, then we're in the second row. It's -1. If the remainder is 3, then I'm third down there, and that's -I. And if the remainder is 0, meaning that my exponent is evenly divisible by 4, then I'm in the bottom row, and that would be 1. So again, look at that cycle. You've heard me say it a few times over already. How about one more, just for good measure? It goes I, -1, -I, 1. Okay, let's go ahead and knock out example 6. We'll do the first 4 relatively fast, and then I'll slow down on the 5th. So, I to the 20th. I could count it out, 1, 2, 3, 4, 5, 6, 7, 8, until I get to 20. That's fine. But I'm going to show you this way right here. So what I would do is just take 20 and divide by 4. And I would say, all right, it goes in 5 times, and the remainder is 0. And so knowing that the remainder is 0, seeing that 20 is evenly divisible by 4, then just as it says right here, then I know I'm the 4th row in my pattern, And the answer, of course, is just 1. I to the 53rd. So what I would do is just take 53 divided by 4. And again, you are more than welcome to grab your calculator here. And if you did 53 divided by 4 on your calculator, you would get 13.25. So what that means is 13, and in the 0.25, 0.25 means 1/4. So it means we're 1 more in our cycle of 4. So the remainder is 1. 13 times, and we're 1 left over out of the 4. Well, of course, if my remainder is 1, then I know I'm in the top row, and it's just I. Alrighty, next one. I would do 79 divided by 4. So rather than having to count out all the way to 79 through the cycle, if we just divide by 4 here, well, if I do 79 divided by 4 on my calculator, I would get 19.75. Well, what does that 0.75 mean? It means that we have a remainder of 3 out of the 4 left over. And so again, the remainder is 3. That means I'm third down in my cycle. Negative I does it. I to the 46th. So 46 divided by 4. And if I did it on my calculator, I would get 11.5. Now remember, we're dividing by 4, so I don't think of that 0.5 as 1/2. I think of it as 2/4. So because we're dividing by 4 here, so it's 11, and I see that 0.5, so remainder is 2, and so negative 1. All right, just wanted you to see one of each, how that plays out. Now this is a good one right here. I to the negative 27th, we have to be a little careful here because it's a negative exponent. How do I deal with a negative exponent? Well, I'm writing it down already, so you know this. We're supposed to put it in the denominator, right? We make it positive by bringing it on down. And now I think about, well, the 1 over is fine, but what is I to the 27th? So this one I'm going to shortcut a little bit, but if I went through my cycle of 4 and figure out, well, where is 27? Well, it would be the third one down. So if you did 27 divided by 4, you would get 6.75. You get 0.75. So remainder is 3, and so we get negative I. All right, now that looks good. We'll stop for a moment. And I get 1 over negative I. But the problem is, am I ever allowed to have I in the denominator? No. So, no I in the denominator. Let me say it one more time. No I in the denominator. So how do I deal with I in the denominator? Well, you can see I already went back to my previous board. How do I deal with just a I in the denominator? Well, again, it's pure imaginary, so can I just do I over I? Absolutely. And that's what I'm going to do. So I, 1 times I on top is I. Negative I times I would be negative I squared. Ooh, here's a great question for you. What is negative I squared equivalent to? Well, I squared is negative 1, so the opposite of negative 1 is just 1. So it's really just I over 1, and look at that. Now look, you can come up with some patterns with these negative exponents. To be honest, I'm not going to give too much away. Here's sort of the formal approach. But if I asked you what I to the negative 27th is equivalent to, it's equivalent to I in our cycle. Okay, good deal. Next, and getting close to the last piece, simplifying square roots of a negative. So we're going to use something you did in geometry in Algebra 2. We're going to use the product property of square roots. And again, you should have some background with this. And just kind of remember that really, when we get that square root of negative 1, that's equal to I. So this allows us now just as a single value to represent square roots of negatives. All right, let's get into letter A. square root of negative 25. Using the product property, this is how it works. So now square root of 25 is, 25 is a perfect square, so I'm going to leave it like that. But I would think of this as, using the product property, 25 times negative 1 is what gives me negative 25 right here. And so this is the product property. I can take any two values that multiply to this and keep them under roots, and it's equivalent to this up here. Now the nice thing is, what is the square root of 25? It's just 5. What is the square root of negative 1? It's I. So now we are representing our imaginary number as opposed to the square root of a negative. So guys, I hate to say it, but we're never going to represent our values as a square root of a negative. You should always be able to pull out I as a factor. All right, letter B. Now, just have to know your perfect squares. There are probably some other ways to pull this off, but I think of the perfect square that goes into 24, which happens to be 4, and it's 4 times 6. So using the product property, the only difference between what you did in geometry and what I'm doing right now is, because it's the square root of a negative, I'm including the negative 1 as a factor and keeping it under root as well. And so I get 2 square root of 6 times I. Now if you left it like that, that's totally fine. The other way to write it, which you probably see a little more often, is the 2 in the I and then the root on the back. So either one of these is absolutely fine. What is not fine, unfortunately, would be this. The I is not under the root, so just make a note to yourself. That would be wrong, and please be very clear. When you write that I is its own factor. It is not underneath the root. It is equivalent to the square root of negative 1, but it is its own value. All right, letter C. And I hope you don't mind me going relatively fast here. If you need me to help you a little bit with some of these square roots, that's fine. But just in terms of, hey, I'm looking for the largest perfect square that goes in 80, happens to be 16 here. And so I would personally write this as a product of these three factors, because then I know that's 4, that's square root of 5, and that's I. So as I said, you can write it like that. You'll see me probably write it more like that. All right, so square root of a negative, please do make sure you pull I out as a factor. Absolutely. Now these, we're just representing a single value. Here we're going to be a little more careful, because now I'm finding all the solutions to these equations. Now in this case, what I'm going to do is I'm going to bring that 36 on over to the other side, because if you remember, we did this. We talked about factoring patterns. I'd love to factor this. These are two perfect squares, but there is no sum of two squares. If this was a minus, we could factor it and get it quickly that way. But unfortunately, we can't. There's no sum of two squares. So I'm going to go ahead and undo the square. That's a great little algebraic technique when there's no x term in the quadratic. Here I get my x. Now because it's an equation where I'm undoing a square, again, different context, because it's an equation, I do take the plus or minus here. Now I have to be able to evaluate square root of negative 36. So I'm not leaving it as a square root of negative 36. But what I do know is the square root of 36 is 6, so the square root of negative 36 has to be the 6i. Awesome. Now, again, it's up to you. You don't have to do this. But if I did that, it would work. If I did that, it would work. Those are your two solutions. All right? Because, I want to get moving here and wrap this on up for you. I'll skip the whole calculation here, but if you want to look at that on your own, please feel free. All right, last one, letter B. So unfortunately, we can't go ahead and undo a square. We're going to have to complete the square here. This does not factor, by the way. And again, we'd always look to factor first, but it doesn't factor. So let's complete the square. Some good practice for us. So bring the 2 on over to the other side. And you should be really good at this stage. 2 divided by 2 is 1, and 1 squared is 1, so I know that goes there. And we factor this. The whole reason, of course, for completing the square the way we did is because of the way it factors. It should be x plus 1 times x plus 1. That's just negative 1 over there. And now I have it in the form I want, so I'm ready to undo the square. This becomes x plus 1. Because I undid the square in the equation, never forget, guys, that's a plus or minus right there. And now I need to evaluate this right here. Square root of negative 1. Hey, everybody, it's just I, by definition, isn't it? And then as a result, subtract the 1, just make sure. So we would write this as negative 1 plus I, but also negative 1 minus I. And if this solution set throws you off in any way, do let me know. But that you should be comfortable writing it like that right there. Real part, imaginary part. 2 different numbers. Negative 1 plus I works. Negative 1 minus I also works. All right, everybody, I'm going to wrap it up right there, allow you to get some good practice with this. Please do let me know if I can help you in any way. Thanks.